first off, let's get a few facts on the board. These are facts about exponents that we have seen before, but we are going to use extensively today. So a to the u. Now, we're going to assume a is a positive number, something bigger than 0. Just like we have been, right? We're thinking about logs and exponents and stuff like that. The base we've been talking about being a positive number. Okay, u is any number or expression. Okay, and a of a to the u and a to the v is the same thing as a to the u plus v, right? And let's just be explicit about that. Like, in other words, let's like once again prove this to ourselves, right? Like, for instance, if we had a to the 2 times a to the 3, this says that this is the same thing as a to the 2 plus 3. And is that true? Well, yeah, a to the 2 means a times a. A to the 3 means a times a, right? And so we have a total of 5 a's. So that's a to the 5th, which, oh, lo and behold, happens to equal 2 plus 3, right? So that's where that nifty little fact comes from right there. Okay? And it's true for any u and any v, doesn't matter if it's an expression, right? And we saw that before where we had 3 to the 2x squared minus 5x plus 3 equals something. You know, this, whatever goes in the exponent, it might be a big, ugly, complicated thing, but we could say, you know what, let's make this a little less complicated and just call this whole shebang u. And that's what we mean by this. So u can be something that evaluates to a number, but it might be really ugly and complicated. But this is always true, no matter what. And it's not just true with integers, right? Like whole numbers like this, because we've gone beyond and we've said, well, what if we want to raise something to a fractional power or something like that? And so we've just demanded that for mathematics to be consistent, that it doesn't matter if you're plugging in an integer or a negative number or a fraction or an irrational number, we still demand that this equation holds. And so that's our first fact that we're going to be using today. The second fact is this one. I'm going to write it like this. A to the p, or actually, I do want to do it this way. A to the q, some number a raised to some power q, and then you take that and raise it to the power of p, is the same thing as a to the q times q. And to be explicit, right? If we have some number a and we square it and then we take that number and cube it, this thing here says, well, a squared is a times a. And we do that 3 times. And so that's the same thing as a times a total of 3 times. And so we have 2 a's 3 times. That's, well, 6 of them. But what's another way we could do that? Oh, it's 2 a's 3 times. That's 2 times 3 is the total number of a's. You end up with 6 a's. That's what that thing means, right? And that's true for any power, whether it's a whole number, whether it's a negative number, whether it's rational, irrational, doesn't matter, right? That we demand that has to be true. That's a property of exponents. Okay. Now, here's a nifty thing. The reason I did it this way is because later on in just a minute, we're going to do this. I'm just going to reverse that order, right? Q times P is the same thing as P times Q. As we can see right here, there's nothing special about the 2 going on the left-hand side. I could have written that as a to the 3 times 2. And if we're so inclined, we're not going to use this today, but it is true that a to the 3rd squared is exactly the same thing as a squared to the 3rd. And that's all we're doing there is just flipping those exponents or just flipping the order of multiplication, which you could do because multiplication is commutative. That's what commutative means, that you could do it in either order. So nothing new, just a lot of review so far. Okay, I'm going to get rid of this. Now, there's two other facts that are going to be useful today, and we saw them last time. I think the time before that, but it's a raised to the power of log a of anything is equal to whatever that is. And so again, I'm going to use, how about z here? Again, I don't want to use x's and y's because when you think x's and y's, you know, you have a certain, in your head, you think, oh, that's some number. Here, I'm saying it's any expression, anything, right? So any expression you put in a log a of z comes back out to z. So for instance, if I have a log a of, how about, I don't know, the square root of x squared minus 1 over, I don't know, x to the 5th. Doesn't matter, right? We're going to use this right here and say, oh, that's just whatever that is. And so whatever shows up here, that's my z. That's the thing that this entire thing equals. In this case, my z is a complicated expression. Whatever. We just don't want to get changed to the idea that this has to be one and only one number. This is, yes, indeed, it is one and only one number, but it's a bit more complicated than that. And so there you go. Okay. And the last thing that we're going to use today is going to be, well, the opposite of this, right? It's when you take log base a of a to any power at all, and I'm going to use w as that power, then this basically undoes what you just did. That gives you back w. We're going to use these extensively today to prove a few theorems about logarithms that we're going to use in the homework. So let me know when you got these written down. Okay. So now here's an interesting thing to note. And this is going to sound weird at first. And you don't really, I would say just pay attention to what I'm doing. You don't necessarily need to write this down, but this is an interesting thing is going on here. If we think about the function f of x equals a to the x, then this thing right here, a to the u plus v, is the same thing as thinking about, okay, I had my function a to something, and I put in a sum. Just like that, right? That's all that means right there, right? Saying, in other words, when the input is addition of two numbers, then we have this really nifty property right here, a of v. That's a of u, a of v. That's all that is. All I've done, nothing fancy going on here, no tricks up my sleeve. I'm just saying that you plug in a sum. Well, that's what that means. It's a to the u plus v. And it turns out to be the fact that this thing splits up like that, which we could rewrite as this, f of u times f of v. And a nifty way of saying this in math speak is to say that addition goes over to multiplication. That is, when the thing that you're plugging into this special function is an addition, then it's the same thing as multiplying the individual outputs. So think about that. The addition of inputs is the same thing as multiplying the outputs. Okay, this is This is not something that you need to memorize. It's just, let's think about this for a second. We're trying to get properties of logarithms. And we know that a logarithm is the inverse of this exponential thing that we're talking about. And the inverse of something is where you basically swap the roles of inputs and outputs. So it makes sense here that in this case, when we're talking about addition of inputs goes over to multiplication of outputs, then then the log, since a log is just the inverse of this, right? A log is you take the inputs and you call them outputs, you take the outputs and you call them inputs, then it should be exactly the opposite case. Like a log should have the property that multiplication of inputs, right? We're just swapping everything here. It used to be addition of inputs goes over to multiplication of outputs. Well, if we're just swapping everything, it should be multiplication of inputs should go over to addition of outputs. So it should be something like this. And I'm being really abstract and high level here by saying, basically forget about the details. We're just thinking about you have some function f and it has this property. Well, then its inverse, we're going to call it g, should have the opposite property. It should be the case that if you multiply inputs of the inverse, then it should go over to addition of output. We're basically saying the same thing here. We're just, again, like that's what a logarithm is, right? It's like saying the same thing as an exponent, but we're just swapping the roles of inputs and outputs. So what's true for the outputs of one should be true for the inputs of the other. That's all I'm saying here. And this formalism here is not really necessary. I'm just kind of using this idea to guide me here to say, well, it should be true. Can we figure out a way of that being true? And that all comes from this nifty little equation right here. So that's where I'm going to begin. I'm going to try to get something like this. That's kind of the idea, is to find a dual statement of this thing, but only in terms of logarithms instead of exponentials. And it should give me the opposite conclusion here, that multiplication of the inputs should go over to addition of the outputs. So this is how we do that. I'm going to say, okay, all right, let's start with that initial equation right here. A to the u times a to the v is equal to a to the u plus v. Now, since my whole goal here is to deal with, now this is where you absolutely want to be taking notes. My whole goal here is to turn this, is to get this thing in terms of logs. So I'm going to say, okay, what I'm going to do then is, well, let's define a couple variables. I'm going to break this into parts. I'm going to call a to the u. I'm going to say that thing is now equal to x. And I'm going to say a to the v. And I'm going to give it a new name, and I'm going to call it y. And since we're talking about log, let's rewrite these as logs. So help me with this first one. This x equals a to the u should be log base something of something equals something. Help me fill in the blanks here. This is your homework.
Log base a times x equals.
Are you multiplying? Wait, what?
Oh no, of x equals the u.
U. There we go. And similarly, let's do this one. What is this?
Oh, oops, hold on. I wrote it down wrong.
Okay.
A equals. Okay. Equals u. All right, and then this one will be log base a of y equals v.
There you go. Perfect. Okay. Oh man, one thing. See, I was planning on talking about that thing at the beginning, and I said we're not going to talk about that thing. There was one point I really wanted to stress, and that's we're very much used to, if you have, say, an equation like this, x squared equals 4, we have not even really, like, without thinking about it, we just kind of said you can take the square root of both sides of an equation. That's true, you can, and it stays true. We simply take the square root of both sides of this to solve, assuming that x is positive. That's how we go about doing this. The same thing is true for logarithms. So in the same way that you could take a square root of both sides of an equation, you can just as easily take the log of both sides of an equation. So if you had, for instance, x equals 4, and then you took the log of both sides, and you said, okay, well, how about let's take the log base 2 of both sides. That's perfectly true. Everything remains perfectly true right there. Log base 2 of 4. I just kind of want to prove or suggest why this is true, right? This is also part of your homework. We change 4 into 2 to some power in order to evaluate this. So log base 2 of x is equal to, what is this? What does this evaluate to right here?
Like, what does it equal?
Yeah, that equals some number. Log base 2 of 2 to the 2 equals what? If you're confused, the answer is right up there in our box.
2.
Yes, because it's whatever this thing is, right? And so that equals 2, right? I just used this right here. We said, oh, it's log base a of a to the whatever. Oh, you just undid what you did. 2 should be the answer, okay? And so, yes, you can take log, any log. I chose to take log 2, but you could take any log of both sides of an equation and your thing stays true. And let's just see if that's true. I'm going to translate this equation into an exponential form. And that means, okay, 2, right? The base is 2 raised to the power of 2 is equal to x. Is that what we started with? Is 2 to the 2 equal to x? Yeah, x is equal to 4. That's so I really did something very trivial here. If you're scratching your head going, what's the big deal? That's what I'm trying to show you, is like, you can take the log of both sides of an equation and everything stays true. It's not in the same way as you could take the square root of both sides of an equation, everything stays true. We're going to use the same principle here with logarithms. And I'm just about to do that here in our proof. So, okay, what did we have? We had some identity involving exponents, and I'm trying to turn this into a dual identity involving logarithms. And so what I did is said, well, let's turn the exponents in terms of logarithms. We could do that. But that's going to come in a little bit later. What I want to do right now, the actual log part's going to come in later. I'm going to say, well, if a to the u is equal to x, I'm just going to replace this guy with x. If a to the v equals y, I'm just going to replace this with y. Then that's the same thing as a to the u plus v right there. So no tricks up my sleeve, really. I'm just saying, all right, we're going to rename that number and that number with different letters. Now, this is where I'm going to take the log of both sides. So I wanted to say that. So it's not like tricky. I'm not changing anything. Nothing crazy is happening. I'm just saying, let's take the log of both sides. And I'm going to take the log base a of both sides. I could take any log. I could take log base 2 if I wanted to. That's not really going to help me. But log base a is going to help me, because now comes where you have to kind of use your brain. The left-hand side, I'm sorry, the right-hand side of this equation reduces to something. How could I rewrite the right-hand side of this equation? And again, if you're struggling, the answer is in the box on the left-hand side.
U plus V.
Just U plus V, right? U plus V is some number. You take A, raise it to that number. It's like 5. A to the 5th, and then you said, okay, well, we're going to take the log of that. It just comes back to whatever it is. So yes, it's just U plus V. U plus V. So on the left-hand side, we have log A. Sorry, log base A of X times Y is equal to U plus V. But U is actually equal to log base A of X. And V is also equal to log base A of Y. And so let me rewrite this in the final bit here. And this is the takeaway. U is the same thing as log base A of X plus V, which is log base A of Y. And that is indeed the dual identity that we've been looking at. This is the way of stating this fact, the original fact that we started off with, but just putting it in the form of logarithms. And it agrees with my intuition at the beginning, which is that it should be opposite, right? It used to be the case that addition of inputs goes over to multiplication of outputs. Well, if that's when we're talking about exponents, so when we're talking about logs, inputs and outputs are switched. And so multiplication of inputs goes over to addition of outputs, right? Log A of Y is the output when you plug in a Y. Log A of X is that number is the output when you plug X into log. And yeah, that's kind of what we were expecting right there. And so that's our first big, I'm going to go ahead and erase the proof and then put this, our final result up here, because we are going to want to keep it with us. So am I ready to erase this stuff?
Yes.
Okay. So that is the first property of logs that we are going to make extensive use of. And I want you to notice something. There was absolutely no restriction on any of these numbers that we used. Let me write this down and I'll say what I mean by that. Like I arbitrarily wrote down an A, right? There's nothing special about log base 2 or log base 7. A could have been any number. So for instance, if I had, say, log base, I don't know, base 7 of 2 times 3, I could say, well, that's the same thing as, and I'm just going to look at my formula here. That just means log base A of 2 plus log, base 7. Log base 7 of 2 plus log base 7 of 3. These could have been also expressions, right? I could have had log base 7 of x squared plus 1 times y minus 7. And then it would still have broken up like this, because again, we don't want to get in the habit of thinking like these are all single like whole numbers or something like that. These x times y might be really ugly expressions. We might have had something like this. Log base 2 of x to the 1/3 times the square root of x minus 1. In which case, we could say, well, hold up, that's something times something. And so this identity tells me that that's the same thing as, and I'm just thinking, okay, something times something splits up because multiplication goes over to addition. And so I kind of prep it like that and say, okay, that's the first thing that got multiplied. That's x to the 1/3. the second thing that's being multiplied in there is the square root of x minus 1. And so that is what this thing is all about. And so a is arbitrary, x is arbitrary, y is arbitrary. It could be anything. Okay, we good?
Mm-hmm.
Okay, so now there's an interesting thing that kind of follows from this. It's like, well, wait a second. You're telling me that log a of anything times anything breaks up like that. Well, what about something times itself? What about x times x? We'll say, okay, well, let's use this right here and say, okay, well, x times x, multiplication goes over to addition. And so this gives me log base a of x plus log base a of, well, I guess it's x. And here's something to notice. Log base a of x is the same thing as log base a of x. So we could rewrite that. We could say, well, that's just like you have, let's say like one apple plus another apple. That's the same as saying you have two apples, or 2 times log base a of x, like that. Do you trust that? Do you believe that?
Yes.
Okay. Again, I'm thinking about log base a of x is just some number. If some number plus itself is the same thing as 2 times whatever that number is. But then here on the left-hand side, we have an interesting thing going on. Is I wrote that as x times x. I could have written that as x squared. Not quite, no, we're not, there's no pattern to notice yet. But here's something. What if we did this? Log base a of, how about x times x, or how about x times x squared? Okay. Well, again, this breaks down. I could say, well, this is something times something inside a log, and so it breaks up, right? Multiplication goes over to addition. And so that would be log sub a of x plus log base a of x squared. But, well, yeah, I'll just go ahead and write it as x squared. But we know just from a minute ago, we could break that guy down. And I'm going to do it the long way here, just to really drive a point home. Log base a of x plus, I'm going to rewrite log base a of x squared as x times x. So we can be really explicit here. What we're doing, we're just going to use this property one more time. We're going to say, okay, you had x squared. That's the same thing as x times x in the inputs. And so a multiplication of the inputs goes over to addition of the outputs. And so we have log base a of x plus log base a of x plus, one more time, log base a of x. Let me know when you get that written down, and do double check. Make sure you're following these steps that I took. Okay, so right, and now let's just see that we have 3 of the same number plus itself, or a number plus itself 3 times. That's the same thing as 3 times that number. So 3 log a of x. And then on the left-hand side, I could simplify that in the same way that I did before. Log base a of, instead of x times x squared, I'm going to go x to the 3rd. And now I think I'm starting to see a pattern here, right? Like, because of this nifty property that you could split up multiplication, whatever power you raise this to, well, that's how many logs you end up with in your expression, right? We started off with 2 x's in here. That means log ax plus log ax, a total of 2 times. When we had 3 x's on the inside, we end up with log ax plus log ax plus log ax, a total of 3 times. And so you could see, you could imagine that it doesn't matter how many of these things you stack up, right? That if you had any number of logs, like for instance, I'm sorry, any number in your exponent, like let's just say x to the n, we could just peel those off one at a time. You could say, well, like let's say n is a really big number, like 10. We have 10 x's right there. Well, I could split that off into x times x to the 9th. Or in this case, I'm just trying to be general and say, well, n minus 1, whatever that is. And so this is the same thing as log base a. Sorry. And so what does this equal? Well, we could split that off as log base a of x plus log base a of x to the n minus 1. And then guess what? We could split another one off there and another one off there. And ultimately, what are we going to end up with? Well, a bunch of log a x's. Log a x. And how many of them? Well, how many x's did you start off with, right? Like, so for instance, if I started off with, when I started off with 3 of them, I ended up with 3 logs. If I had 4, you can imagine you would end up with 4 logs. If I start with n, I should end up with a total of n logs there. And log sub a of x added to itself, a total of n times would just be n times log base a x. And that's what we have right here. And so you might think, oh, here's a nifty formula that we're going to use. And you're right. The problem is that this does not work. This only works if you've assumed that n is an integer. And whenever we're using just plain old integers like 7 and 3, 2, 10, all of those guys, then yeah, this absolutely is perfectly true. And it follows from this fact right here that you could just keep splitting up powers. But remember at the very beginning of our talk, right? I said, yeah, this could be 2 and this could be 3. And so u could be 2, v could be 3. So then u plus v would be 5. But we don't want to restrict it to just integers, right? We want to make sure that this works for any number whatsoever. And so right now, what we've just shown is this nifty property of logs, but we've only shown that it's true when n is an integer. And so we need to do a little bit more work to get this to work for any number, that's what we really want. Is we want to say, well, what if n isn't a power? Isn't an integer? That the power that you're raising this thing to is, who knows, it could be the square root of 2, it could be pi, it could be 3/4. We want it to work in every case. So this is how we're gonna do it. But it's motivated again by this right here. Like I never would have thought that we would have ended up with something like that if it weren't for this fact right here. So really, right, let's kind of think about what we've done today. We just took an identity of exponents and we said, how can we rewrite that in terms of logs? And we did that. And we said, well, hold up, notice something. That gives us this interesting property when x and y are both the same thing. That means you could split it off. Oh, and so there's something with exponents. And so now that's kind of motivating me to do this next thing is like, can we get that when it's not just pure integers? We're going to start with actually this guy right here. We're going to say, okay, a raised to the log base a of x equals what?
X.
X. That is just the definition of logs and exponents. It's that easy. There's nothing funky going on there. But now what we're going to do is this. We're going to say, let's suppose that P, the letter P, is any number. Because like I said before, the problem was we don't want to just do integers. But we're going to say, let P be any real number right here. That's what we're going to do. Now let's just take it and raise both sides of the equation to the power of P. And like I was saying earlier, you could always take both sides of an equation, take the log of both sides of the equation in the same way that you could take a root of both sides of an equation. And the same way that you could square both sides of an equation or cube both sides of an equation, you could raise both sides of an equation to a power. So there's nothing new going on here, really. It's just this stuff's really ugly looking. But on the left-hand side, x raised to the power of p is, well, it's just x to the p. I'm not going to write it with parentheses there. It's just x raised to the power of p. But now what I'm going to use here is that other nifty property of exponents. And it's that, let's just look at this, right? We're saying you have a raised to some power. Who cares what it is? In this case, it happens to be log base a of x, but we could just call it q. And then we're going to raise that to the power of p. Well, that's the same thing as a times q, a to the q times p. So in other words, that's a to the log base a x times p. And I made a fuss about this earlier, and I even wrote it up on the board. We could do that in either order. And it's just bad form to write something like that. Like in the same way it's bad form to say square root of x times 2. We put the constant out in front like that. Same thing with logs. We don't like to have, we like to put the log at the far right if you can. And so I'm just going to rewrite that with the p on the left-hand side of that. And let's just double check our work so far. All we did is we just started with an identity. A raised to the log a of x is simply x. We raised both sides to the power of p, where p is any number, any real number at all. And we said, okay, well, what does that do? Well, that just gives us x to the p on the left-hand side. And over here, well, by this nifty little property, take something raised to q, then raised to the p is the same thing as a to the p to the q. Sorry, a to the q times p, which is the same thing as a to the p times q. And that's where we ended up right here. So I'm just gonna rewrite this to like this is the point right here, is that x to the p is the same thing as a raised to the p times log base a of x. And now, finally, I'm going to take the log base a of both sides. And so that gives me log base a of, the left-hand side is x to the p, equals log base a of a to the p log a x, just like that. One more time. I told you we were going to use those identities so much. What does how can we simplify the right-hand side of the equation? What does that whole shebang equal?
All right. E times log a px.
There you go. Because again, I'm just using that nifty fact right here. Log base a of a to any expression in the world is equal to, well, whatever that expression is. In this case, that expression happens to be p times log base a of x. And so now what we knew was the case when p was an integer, right? Because of this, right? If p is 3, that's the same thing as log a of x times x, which we split up into 3 separate logs and then say, oh, well, it should just be 3 times whatever that log is. Yeah, we already knew that was the case when p was an integer, but here we've proved it for the case where p is any real number at all, which is cool because this turns out to be the most useful property of logarithms. This is the one that you're going to use all the time. And so I'm going to write, it's so important, I'm going to write it in red. And it will be canonized on the board. Log base A. That's any base A, X, any number raised to the P. Actually, it has to be a positive number. And we've been glossing over that fact. But we've talked before, you can't plug in negative numbers into a log. Actually, you can, you just get complex output. But in our class, we are only plugging in positive values. So I kind of glossed over that. Everything I've done on the board thus far, I've assumed that any number that I put into a log is a positive number. So, but nonetheless, here we go. Now, but so let's just look at this. This is how this is going to be so useful for you. You'll see why, especially in the homework, but just a couple thumbnail examples is if you have something like this, log x to the, I don't know, 1/3. The way that this thing works and the way that I think about it, like this whole property that I just wrote down, log base A of x raised to the P equals P times log base A of x, that thing, the way I think about it is exponents drop out. And that's what visually goes through my head when I see this, is I just imagine that if you're inside a log, it doesn't matter what log. In fact, I didn't even write a base down there, did I? That's how much this doesn't matter. But it could have been a log of anything, right? And so we'll say this was log base 2 in both cases. Who cares? The point is that whenever you see something like this, it means that that exponent right there just jumps out. And that's perfectly good. Also means perhaps that you'd want to go in the other way, right? Like if you had something like this, how about 4 log base 7 of 2? We could rewrite that if we were so inclined by saying, well, if the exponent jumps down, then whatever is in front of it also jumps up. But I think about it in my head as exponent jumps down. And it doesn't matter what that exponent is. It could be, again, a big, ugly expression, something like this. Let's take the log base pi. Yeah, because you could have a base pi. That's perfectly fine. Let's take the log base pi of, how about 3 to the 2x squared plus x? Say, oh man, what is that? Well, exponents drop out. And so that entire exponent, whatever it is, parentheses are your best friend, just drops out. The base, in this case 3, stays put. But what's up there, right? And this is visually what goes through my head is, oh, whoever's up here gets to jump out. And in that case, it was 2x squared plus x. And so 2x squared plus x jumps out. And that's what you have right there. We good to go?
I think so.
Okay. So these are just proofs of these identities that are so very useful when dealing with, well, with everything, right? They show up in all kinds of crazy places and you have to deal with logs. And then you can make your life so much easier in so many cases if you can change something that looks like this into something that looks like that. And so there's one last thing that we want to get right here. And we could do it like this. So we talked about what happened. We talked about how multiplication goes over to addition. We did not talk about division, though. What happens when you divide two numbers inside a log? Let's just see. We have log base A of some number divided by some other number. And what's really nice is now we have enough stuff on the board to actually get a nice formula out of this. So we have log of something divided by something else, we could just say, well, hold on, let's just rewrite this as log of something times something. X times, how about y to the negative 1? Is that the same thing as that? Is it true that y, x over y is the same thing as x times y to the negative 1? That's what negative 1, that's what raising something to a negative power means, right? Like if I just said, what is 2 to the negative 1? You would say, well, 1 over 2 to the 1. And so if I had x times 2 to the negative 1, you'd say that's the same as x times 2 over 1. And so y to the negative 1 is the same thing as 1 over y to the positive 1. Therefore, x times y to the negative 1 is the, oh yeah, okay. So that works. I'm just being a little tricky here, but that works. So now let's use that top property right there and say I have something times something else. And yes, there's powers going on, and maybe these expressions are really ugly, right? Maybe x is actually like 45 plus something, blah, 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 and y is a big ugly thing. But I could break this down and say, well, right now, we'll pretend that you have all your x and all the y is just one thing. I'm going to use that first property right there to say that's the same thing as log base a of the first thing plus log base a of the second thing. The first thing in this case was an x, so x goes in there. Second thing in this case was y raised to the power of negative 1. And now we're going to use our favorite property of logarithms, which is that this number right here drops out. The exponent drops down. And so this gives us log base a of x plus negative 1 times log base a of y. Oh, that's nice, because now we get this. Plus negative 1 times something is the same thing as just minus that thing. And so log base a of x, how about minus log base a of y? And there you go. That's the last identity that we're going to be dealing with today. Log of something divided by something is the same thing as log of the top stuff minus log of the bottom stuff. Okay. Up here. Any questions on that?
Not at this second. I'm just finishing writing it down real quick.
Okay.
Okay. Okay.
Okay. So this is, and to be clear, right, these don't have to just be single numbers. It could be any base and anything divided by anything else. So for instance, if we had something like this, log base 3 of the square root of, how about t plus q over, how about x squared? That's a lot of stuff going on right there. But what I could do is say, well, wait a second, you have something divided by something else. And so I know that that's the same thing as, I know that division goes over to subtraction. You see how I wrote that down before even thinking about what it's going to be? It's usually how I write this stuff down. I notice, oh, wait a minute, log, and on the interior, you have something divided by something else. And so that means that it's going to split up with a minus. That first thing is the square root of t plus q. The second thing is x squared. And so it looks like that. Then if I really wanted to be tricky, or I mean, depending on what you're trying to do, we could actually reduce this more, right? Because of the nifty property of logs, I could say this 2 drops down. And so this is the same thing as log base 3 of that stuff minus 2 times log base 3 of x. And check this out. This I believe is going to show, this is going to show up in your homework a few times, where they want you to simplify this thing as much as possible. And we want to remember that one way of writing a square root is to write it as something to a power. So the square root of t plus q is the same thing as t plus q to what power? I guess I'm asking, the square root of z is equal to z to what power right there? How can we rewrite a square root?
2.
Is it
Z to the second. Z squared.
No.
No?
Well, you tell me, is the square root of 4 equal to 4 squared?
Oh, no. That would, right. So it's, oh.
Mm-hmm. It's not 2 over 1.
So 1 over 2.
Over 2. And so the square root of t plus q could be written as t plus q to the 1/2. And then we could go, aha, that guy comes out. And then we can simplify this guy even further and say 1/2 log base 3 of t plus q minus 2 log base 3 of x. Now, I want to address a couple of possible red herrings before they occur. Let me know when you got that written down.
1 sec.
Okay.
Okay.
Okay. Now, one thing to notice here is that this addition and multiplication only goes one way. It is not true. It is not true. One more time. It is not true that log of something x plus y equals log of something plus log of something. That is not true at all whatsoever. Remember where all this came from. This statement right here is the dual statement of this, that when you addition of inputs goes over to multiplication of outputs, therefore multiplication of inputs to log goes over to addition of outputs of logs. Addition of inputs, we don't have anything to tell us about that. That is, there's no information about that. So So in that last example, when I had their 1/2 log base 3 of t plus q, don't be like, oh, I could break that up more. That's the same thing as log 3 of t plus log 3 of q. No, it's not. That is as simple as it gets in there. You can't do anything more with that because that's not what any of this says. There's nothing about addition of inputs here. Similarly, and this is one that screws everybody up, myself included, is that there is nothing to tell you what to do with this. The division of two logs, there is nothing. That's all it is. That's as simple as it gets right there. Because, right, we get it confused in our heads. You might think, oh, log of this over that, well, that's the same as this. No, not even close. And if you don't buy that, just pick your favorite log based, I don't know, 2, and plug in a bunch of different values, and you'll see it's not the same as doing this and that. And so this is certainly not equal to log b of u minus log base b of v. That is not the case. This is a completely different monster. So you got to be careful that whenever you're going to say, oh, I could split this division up into a subtraction, make sure that it's all inside stuff. So, however, if on the other hand, you had log b of u over v, then yes, it absolutely is equal to log base b of the top stuff minus log base b of the bottom stuff. So be careful. Be very careful with that right there. So, okay, let's do examples from homework. So I'm going to leave the red stuff up here. The green stuff was just to get us to this point right here. So any questions about these dire warnings that I've issued you?
No.
Dire warnings. Okay, cool. So what you're going to do, your homework is going to involve basically repeated usage of these identities. This is what it's going to look like. You're going to be told to express things as a sum of logarithms. Here's one example, number 6. It says express log base little t of 5 times y as a sum of logarithms. And well, it's real simple. There's a 5 times a y. And so this thing just splits up as log base t of 5 plus log base t of y. That's all they're looking for there. And it's a simplify if possible. This one you can't simplify, but they give you ones with like actual, like where you'll end up with a log base 2 of 64. And you know that 64 is 2 to some power. And so then you could simplify that. But in this case, you can't simplify. We don't know what t is. We don't know what y is. We know what 5 is, but we don't know what t is. So that's as simple as it gets right there. So that's one way of going. Then you're going to have to go in the opposite direction too. It's going to say, so you got this?
Yeah.
Okay. It's also going to tell you to go in the opposite direction. So number 8 says take log base b of 65 plus log base b of 2. And it says write as a single logarithm. So we're just doing this in the reverse order, and it's exactly what you think it's going to be. This thing is just log base b. So the sum of logs is a log of the products. And so boom, 65 times 2, whatever that is, I don't care. It's 120, 130, I guess, which we could write as 130. No, we'll just do it. Okay, so that's the same thing as that right there. Another thing going on there. Okay, they're going to give you, so you got this?
Yep.
Okay. They're also going to give you something like this. Here's number 10. They're going to say log base a of x to the third. It's going to tell you to express this as a product. And you know which one this is, right? And this is our favorite property of logs. This is the most useful property of logs, is that exponents drop down. And so we'd say, oh, this is the same thing as 3 times log a of x right there. That's what they're looking for. Okay, you got that?
Yes.
14 is almost exactly the same thing. They're going to say expresses a difference. I'm going to give you something like this: log base t of big T over 7. And we say, okay, hold up. Okay, division. Is it in the interior? Yes, it's in the inside. It's not log of something divided by log of something. It's log of something divided by something. And so we could say, okay, that's log of the top stuff minus log of the bottom stuff. The top stuff is T. The bottom stuff is 7. And we're good to go. Okay. This is where it gets a little tricky. Can I get rid of all this stuff?
Just one. Sorry.
No, no problem.
Okay.
Okay, so. Number 18. These are some of my favorite types of questions right here. They give you this stuff. Log base b of xy squared over z to the third. And they tell you to express in terms of logarithms of x, y, and z. And so in other words, they're looking for a sum and or difference. Sum means difference, but a sum of logs that are basically as simple as possible. The way I like to look at these is the first question I ask myself is it something divided by something? Because if it is something divided by something, well, I know how to deal with something divided by something. So that's going to be the first place I go with this. I'm going to say, okay, well, it's going to take a bunch of steps, but I know that since I have the log of something divided by something, that's the same as the log of the top stuff minus log of the bottom stuff. And so the top stuff is xy squared, okay? The bottom stuff is just z cubed. Okay. So that's just z cubed. There you go. All right. We're part of the way there. Now, okay, I have no more denominators in anything. So the next question I ask myself is, do I have products? I check for dividing. Now I'm looking for multiplication. And I do see, yeah, I do have a product right here. So I'm going to split this guy up right here into something times something is the same as log of the first thing, log of the second thing. And so I'm going to go log base b of plus log base b of minus all this other stuff here. The first thing was just a plain old x. So just a plain old x in the first. Second thing was all y squared. And so he's a y squared. And in general, what I like to do, and this is a good principle here, save your exponents for the very last thing that you do. Try to get rid of all your divisions and multiplications first, and then go into your taking care of your exponents. And that's where we're going to use our favorite property of logs right now. So I have squared here that's going to drop out, and I have a cubed here that's going to drop out. And my final thing that I want is log base b of x plus 2 log base b of y minus 3 log base b of z. There we go. That's it. That's what they're looking for. That's what they mean by that. And the one in your homework, it has a 5 in there. Like there's like a 5 right here. And they say get it in terms of X, Y, and Z. Well, there's a 5 there. So what do you do with the 5? I guess they're also looking for, you should have a log base b 5 by itself, which is, I wish they wouldn't have done that, but whatever. It's an odd problem, and you'll see how they write it, and you should be able to confirm that, yeah, you could get that too. So, okay, any questions with that kind of question?
No.
Okay, the next kind of question they give you is to basically do the opposite of this. They give you an expression like this and tell you to go back to write it as everything is one input, basically. And so, good example of that. I think I wanted to do 20. I did want to do 20. Okay, so number 20, they give you 1/2 log base a of x plus 3 log base a of y minus 2 log base a of x. Now, the way I like to do these is to get all, like, it's in the opposite order. Since I like to save exponents for last to break it up, I like to do exponents first. If you wanted to, you could say 1/2 of log ax minus 2 log ax's, and then say 1/2 minus 2 is whatever, and you'll end up at the same place. I personally like to just do it in the opposite order and get rid of my exponents first. And so I'm going to take each one of these and throw him up into the exponents and say, okay, 1/2 times log is the same thing as throwing that 1/2 into the exponent. 3 times log of something is the same thing as throwing that into the exponent. Careful with that minus sign. Minus, instead of a 2, I have the 2 up in the exponent. Follow that?
Yeah.
Now I could go ahead and do, and I like to do addition first and say, all right, all of the adding logs, well, I know addition goes over to multiplication. So I could say that's the same thing as log base a of, and I'll just combine those two together and say it's that thing times that thing. So I have x to the 1/2 times y to the 3rd in there, minus log base a of x squared. Finally, okay, subtracting logs is the same thing as this. And so this thing is the same as having that stuff divided by that stuff. And so that's the idea here, is you have a sum of logs and we want to turn it all into one log. And so I'm not going to use my brain. I'm going to say, well, whatever that stuff is goes on the top. That's x to the 1/2, y to the 3rd. Divided by whatever that stuff is, it's x squared. Technically, we're done because we've put it all inside one log. That's all they ask for, but I could see that, okay, I have 1/2 of an x on the top. I have 2 x's on the bottom. I guess I could write that as 3/2. Log a, I'll be left with 1y on top and x to the 3/2 on the bottom, because that's an x to the 1/2 on top and x to the 4/2 on the bottom. One of them cancels. It leaves me with 3/2 on the bottom, x to the 3/2. We could write that a few different ways too. I mean, we could keep doing this. We're pulling out powers and whatnot, but I think this is probably what they have in the back of the book right there, or something like it. If at any rate you get down to here and they have something in the back of the book that's not exactly that, you should be able to say, well, hold up, what, can I do some canceling? Yeah, okay. And then I end up with this thing right here. All right. Good?
Yeah.
Okay. So then the other type of problem that they have is they say, yeah, Nah, we're not going to do. I don't want to do those. Those suck. It's not useful. Okay, so we have these types of problems. Number 42. It says to solve, and they give us 8. Give yourself some room. 2 times log base 8 of x plus log base 8 of x equals 27. And you go, what? But the idea here and what I'm thinking, the thing that's going through my head when I see this is I know that if I could get 8 log 8 of just stuff, if I could get that stuff by itself, then whatever that stuff is, well, that's an identity. It just comes out, right? Like we had that on the board earlier. A to the log A of Z is just Z. So 8 to the log 8 of stuff is whatever it is. And so that's kind of what I'm hoping I could do here. Problem is, well, now we got to convert that into 1 log, which is, well, that's what we just did. That was the type of problem that we were just working on. We had an expression full of sums of logs. So I'm going to do that again in the way that I like to do it. I'm going to get my exponents out of there first. So I'm going to take this up into the exponent to give me x squared plus log 8x. Like that. And then I say, well, the sum of logs is multiplying the inputs. Just going to use this one in reverse and say, okay, I guess that's the same thing as 8 to the log 8 of x squared times x, which is just x cubed. Let me know when you got to here.
I'm there.
Okay, and so 8 to the log 8, well, that's just x cubed. So that's 8 log 8 x cubed equals 27. And that was the whole point. That's where I was trying to go with that. 8 log 8 is an identity. And so that's the same thing as x cubed equals 27. And I think you know how to solve that guy right there. There's the homework. All right. Any questions before we end?
I don't think so.
It's tough stuff. I mean, like but I think you have enough examples to go with. Some of them might trip you up, and roots, write them as powers of exponents, just like I did earlier, right? With the p plus q square root, we say, it's the same thing as p plus q to the 1/2. If it were a 5th root, we'd say it's to the 1/5 and stuff like that. But that should be enough